Now that you learned about the physics of ultrasound, I will show you that these ultrasound waves can be used for many different things in echocardiography. Echocardiography, as you probably know, consists of many different components, and the first component I would like to discuss is two-dimensional imaging. The camera doesn't make a bit of difference. All of them can record what you are seeing, but you have to see. This is a quote by Ernst Haas, who is one of the greatest photographers of all times, and it is also true for ultrasound. We'll be talking a lot about technical stuff and how images are created. But keep in mind that it is you, your experience, and your capabilities to interpret images which really makes a difference in the end. But first, one step back. We have to understand the principles. In the previous chapter, we discussed how the ultrasound wave is reflected when it hits a boundary. But how can we now build an entire image with the help of ultrasound? Well, to do that, we need not only one transducer or one crystal, but we need several, many as a matter of fact. And each of these crystals fires a beam and then waits if a reflection and when the reflection returns. And it does that one after the other successively. Now in a normal image, you will not notice that. It just goes so quickly that you have an entire picture in an instant. But on each boundary, we'll then get a reflection, and that is processed to an entire image. Depending on how the ultrasound rays are emitted from the transducer, we can distinguish so-called linear array probes from curvilinear array probes. In linear array probes, we have a parallel orientation of the ultrasound beams. Therefore, the ultrasound field is just as wide as the footprint of the transducer is. In other words, the width of the transducer. This is not the case in curvilinear array probes, where we have a fan-like expulsion of ultrasound rays. Here we have a smaller footprint than the field actually is. Therefore, these transducers are ideal for cardiology, where you have small intercostal spaces and where you do not have very much room to place the transducer. So, in cardiology, we mainly use curvilinear array probes. And here's a beautiful example of an ultrasound image. You can see again the shape of the sector, a curvilinear array probe, and you can see that there are light and dark areas. The light areas, or the white areas actually, are those areas where we have a lot of reflection, while those which are dark don't. Thereby we can really distinguish tissue from each other. Tissue which has a lot of echogenicity and tissue which doesn't. Do you all recognize what this is? Well, obviously this is not a heart, but it's a fetus. But the same principles apply to all types of ultrasound, no matter where you use it. So, ultrasound is a cut plane technique. This means we're looking inside a structure or inside an organ. Now, this makes the interpretation of ultrasound sometimes quite difficult, because you have to have a good understanding of the true shape of a structure, and you have to kind of internally reconstruct the images and the cut planes that you see. But it also has the large advantage that you can see into an organ and see what's going on inside. The 2D image quality in echocardiography has made a tremendous leap in the last 2 or 3 decades. I can still remember the first images I saw was probably sometime around 1985 or 86, I guess. And at that time, I had the impression what people were doing with echocardiography was more like guessing. For example, at that time, I never really was able to really see the pulmonic valve. Now you can see it in every patient. But what makes good image quality? What are the criteria? Well, it's spatial resolution, contrast resolution, and temporal resolution. First, I would like to discuss spatial resolution. Now, spatial resolution can be divided into lateral and axial resolution. Lateral resolution is defined as the ability to distinguish between objects which are on the same line, or in other words, at the same depth, while axial resolution is defined as the ability to distinguish between objects which are on the same axis at slightly different depths. Here's an example of a phantom that has been scanned with 2 different transducers. On the left-hand side, a transducer with a low lateral resolution, and here with a high lateral resolution. Look at these points here. These imaging points are much more blurred
in this situation, and it's even impossible to distinguish that there are actually more than one image points. So this is lateral resolution. But what determines lateral resolution? Well, basically it's the beam width and the line density. We'll talk about that later. The imaging frequency and also the gain settings. Here's another phantom which shows you the effects of axial resolution. On the left-hand side, we're imaging with a fairly low frequency, 6 MHz, while on the right with 12 MHz. And the difference is very apparent. We have blurring and confluation of these imaging points, while we do not have that in this example. Also take a look at the background here. This image is much sharper. Even details are apparent. So axial resolution mainly depends on the imaging frequency, but also on the pulse frequency. So the lateral resolution largely depends on the number of scan lines you have. And good transducers have high scan lines, and poor transducers have few scan lines. But there's a limitation as to how many scan lines you can use, simply because we always have to wait for a return signal until we can send out the next scan. So in a way, frame rate limits the number of scan lines we have. And then there's another limitation. It's just a physical limitation of how many little crystals you can put in the transducer. It does get quite crowded in there. Would you fit in that pool? Would you even want to fit in that pool? Do you think I did? Well, find out for yourself. But aside from the absolute number of beams that we have, it's also important how wide these beams are. In other words, what the beam width is. This illustrates the problem. If we have very wide beams, then a structure, this structure here, would be hit by two beams. And thereby, the system would think they're two separate points. Opposed to a situation where the beam width is very narrow, and then we only have a distinct reflection from one beam, and thereby a correct representation of the actual situation. Now I would like to help you understand the importance of the ultrasound pulse and how it affects the image resolution, both the lateral and the axial resolution. When we are generating an image, we are sending out a pulse. This pulse is reflected, and from the time it takes to return back to the transducer, we can then calculate where this reflection has occurred. Now we have to wait until this pulse returns until we can send out the next pulse. So we have intervals between the different pulses. Now the shorter these intervals are, the better the resolution. But what influences now the intervals between the pulses? First of all, how far is the structure away from the transducer from which it is reflected? And then second, how high is the frequency we're using? Because if we use high frequencies, we have shorter wavelengths, and thereby we can make shorter pulses. So that also affects basically the intervals. This again explains why we have a better image resolution if we have high frequencies. And remember, the shorter the intervals between the pulses is, the more rapidly we can fire one beam after the other, and therefore we also enhance the lateral resolution.
So you can already see that there's a very strong interplay between many different factors in ultrasound. The pulse width, the pulse frequency, the imaging frequency, the lateral resolution, the resolution altogether, and also, of course, the frame rate.
Another important criteria for good image quality is contrast resolution. And contrast resolution is the ability to discern between different grayscale values. On the left-hand side, we have an example with very high contrast resolution. You can see many details here, detailed gray values, while we do not have that here on the right-hand side. In other words, we're losing information in this image here. Another factor that influences the contrast resolution is acoustical noise. This will be discussed later. The grayscale is the number of gray values which are displayed, usually 256. However, keep in mind that the human eye is not able to really see such many different shades of gray. We can only see approximately 32. Now I just briefly have to go back to the physics of ultrasound again. Remember I told you we're sending out a signal which has a certain frequency, and that wave, that pulse wave, is reflected. What I haven't discussed yet is what the frequency of the return signal is. Well, the basic frequency of the return signal is the same as the one that is sent out, but not entirely. Take a look at this curve here. And if you see this curve, you can see that it's kind of skewed. The reason is that we have a second curve or a second frequency component within the spectrum. And this is the so-called nonlinear harmonic spectrum, or also called second harmonic spectrum. The reason we have second harmonics is because the ultrasound wave which hits the tissue causes the tissue to swing or resonate, and thereby another wave or another frequency is also emitted, which is usually a multiple of the initial frequency. So this wave is what we call the second harmonic wave. The neat thing about ultrasound is that we can then decide which component of the return signal we're going to use for further processing. Either we use the component which has the same frequency as the send frequency, then we call it fundamental imaging, or we can filter that out and only use the harmonic component, then we call it harmonic imaging. But why would someone want to use only the harmonic component, which obviously has a much lower amplitude? The reason is quite clear. The image quality is better. We have much less artifacts. But now it's time that we go to the ultrasound machine, where I would like to show you exactly what the influence of harmonic imaging and the imaging frequency on the quality of the 2D image is.
Harmonic and fundamental imaging gives us a bit of a different characteristic of the image. Here's an example. On the top, we have two different frequencies of fundamental imaging, and on the bottom, we have two different frequencies of harmonic imaging. You can see that with harmonic imaging, usually the cavity and the heart chambers themselves, or the inside of the chambers, are dark, while with fundamental imaging, we have more artifacts or speckles within the image. The other thing we see is that with harmonic imaging, we have a better endocardial delineation, and the valves also appear a bit thicker or more blurred. But in general, as you will probably also agree with me, the image quality is better with harmonic imaging than with fundamental imaging. So far, we only saw and talked about still images. But with echocardiography, we're also interpreting moving structures, such as heart valves and the myocardium. So it's very important to also understand how moving images are created and which factors influence them.
To understand how moving images relate to the quality of ultrasound, it's important to use the term frame rate. Now, frame rate is defined as the number of images, or the number of pictures actually, which are displayed within 1 second. Just to give you a better appreciation, in PAL television we have frame rates of 25 frames per second, while with HDTV we have frame rates of 60 pictures or frames per second. And what can we achieve with echocardiography? Well, frame rates above 200 frames per second, and with experimental ultrasound even more, probably above 2000 frames per second. But the question remains, why do we need such high frame rates in the first place? They're higher or quicker than what our eye is able to grasp. Well, Marion is going to show you now in a demo what it is good for in ultrasound.
So I'd like to show you now something about reviewing the images and what is the advantage of these high frame rate images. You see here I have already stored an image from the mitral valve with a high resolution zoom with 109 frames per second. If I just recall the image and look at the valve, looks nice, but actually, to say the truth, the eye cannot look fast enough to detect the real very small motion. So we cannot separate these 109 frames. So what to do? You have two possibilities. You can either look at the image in slow motion, so just take the trackball and remove a little bit the speed of the image. And you can see very nicely here how the valve is opening, there's some movement, and then it's closing. So then you can really appreciate the high frame rate and the small details of the movement here. You can also just freeze the image, so stop it, and then go with the trackball, go frame by frame to the part where you are mostly interested in. You see here, for example, I'm interested in this part now, and then you can just scroll back and forth. This might be interesting in valve movement or when you have some endocarditis or something. Everything which moves very fast, it's very nice to have the high frame rates, and then in the review mode to go with slow motion or frame by frame.
So a number of factors influence the frame rate. The sector width, the frequency, the number of scan lines we have, and also the imaging depth.
And finally, I would like to briefly discuss some of the limitations of 2D imaging and of ultrasound in general. In particular, I'll talk about attenuation, about the influence of various tissue, and then we have a specific chapter for you on artifacts. We already talked about attenuation in the chapter on the physics of ultrasound. Just for review purposes, attenuation is the decrease in amplitude and intensity of the ultrasound wave as it travels through a medium, and it is caused by absorption, reflection and refraction, and by shadowing. Basically, attenuation is the transfer of energy from the beam to the tissue. And I mentioned earlier, and I cannot mention often enough because it's very important, absorption is proportional to the imaging frequency. In other words, if you have high image frequencies, you will not penetrate very deeply. And if the ultrasound beam hits a structure where we have a lot of attenuation, as for example here where we have a gallstone, then no ultrasound rays can pass through and we'll have what we call shadows. The variability in attenuation from one ray to the other can also cause a phenomenon which you might call pseudo-enhancement. Here we have a cavity which has a fluid inside, and thereby there's not very much attenuation. So when the ultrasound rays pass through this structure, there's still a lot of energy left, and therefore we have more bright echoes than, for example, here on the side where this reduction in attenuation did not occur. The nice thing is that we can manipulate the way the image appears on the screen. In other words, we can amplify the return signal by using the so-called gain function. I will show you in the subchapter on how to optimize your image how this is done. But even the gain button won't help you if you're confronted with the biggest enemy of ultrasound, with air and with bone. Why is this so? Well, while with normal tissue we also have some degree of absorption and reflection, but still most of the ultrasound rays can pass through and penetrate deeper into the tissue. This is not the case if we have bone or air. If we have bone, there's very much absorption, and if there is air, we have very much reflection. In both instances, the result is the same. The ultrasound rays do not pass through. Why is this a particular problem in ultrasound? Very simple. Because we have the rib cage and we have the lung which surrounds the heart.
But now I would like to show you some short video demonstrations of what happens if we encounter air and bone in ultrasound. Where is air a problem in echocardiography? The lungs. Here's an example. We have beautiful image quality, but as soon as I ask the patient to inhale, the heart is gone. So we're now trying to image the heart through the lungs, which simply doesn't work. As soon as he exhales, the image is there again. So air is no good. The second enemy we have is bone. Here we have an image. As soon as I move the transducer towards the sternum, the image is gone. So we have a black image. We just can't see the heart, even though the heart is obviously behind the sternum. So the second enemy is bone. So this concludes the subchapter on two-dimensional imaging. With all this information in the back of your head, in the next chapter we will turn to how to optimize the 2D image on the ultrasound machine.